Selected error control codes, part 1, simple codes, single parity check, product and repetition code. Single parity check code uses a single parity check bit to generate code word with an even parity, means even number of non-zero bits once. Then its code word length is number of information bits plus 1, and parity check bit is sum of all information bits. In decoder, all bits are checked. If the modulo to sum is 0, then decision is no error. If 1, then decision is a single error. Code detects not only occurrence of single errors, but also all other odd numbers of errors, triple errors, for example. The probability of erroneous decoding is a probability of double errors plus probability of quadruple errors, which is much less than probability of double errors, and we may say that the probability of erroneous decoding is probability of double errors. Here we have a code for three information bits, 3 messages encoded in this code. This is a parity check bit. As you can see, we have 8 redundant words of the length of 4, which are not code words. Then the total number of transmissions is 128. 8 multiplied by 16. Errorless, obviously 8. Erroneous, the remaining 120. Among them, undetectable errors if one code word becomes another code word. A number of these undetectable errors is 56, which means that detectable errors, number of them is 64, and 8 of them can be corrected using these redundant words. For example, we may assume that all errors with the error pattern error at the first bit is corrected. If so, then this sequence word received can be corrected as 1001, as W4, and so on. Another simple code, a product code. A single parity check code has no error correction capability. Its minimum distance is 2. Then error correction can be achieved by combining 2 single parity check codes. And the information word is written down in rectangular array. Product code parameters, first of all, its minimum distance is 4. It's a product of minimum distances of both codes, which is 4. Then such code may detect all triple errors, or detect all double errors and correct all single errors. And actually this property will be used, this option will be used. Decoder decision is based on syndromes, parity check sums of individual rows and columns. Let me show you an exemplary code combination of 7, 6 and 5, 4, which means that in total we have 24 information bits. They are written down in this table of 7 rows and 5 columns. These are check bits for columns, these are check bits for rows, and this is the overall parity check. Let me study at first some exemplary information sequence in these positions: columns from 1 to 4, rows from 1 to 6, then supplemented by parity check bits for columns, for rows, and overall parity check is 0. Then we have 2 options. The first one is a detection of all triple errors. If any of parity check sums is 1, then we have a triple error or error, detectable but not correctable. In case we have designed our decoder to detect every and correct every single error and detect double errors. In case if in one column, in one row we have 1, then it's easy to point the erroneous bit. In case of double error, also it is possible that parity check sum are one in 2 rows, 2 columns, and then detection is made but not corrected. An exemplary transmission. Let me assume that erroneous bit is here, crossing of the 2nd column and 6th row. Then a parity check sums are 1 in this 2 in this column, this row, and this points the erroneous bit, which can be corrected from 1 to 0. Another transmission, double error. We have this error in 2 different rows, 2 different columns. Then we have parity check sum in this row equal 1, and in this row 2 columns equal 1, and if so, the decision is that we have double error, detectable but not correctable. Now triple error. Triple error 1, 2, 3. In this case, please observe that we have the same effect as for a single error, but this is not a single error. Then if the decoder is designed to detect every triple error, then decision is question mark. W star is question mark. However, if decoder is designed to detect and correct single errors, then decision is incorrect. And the last one, simple code, is a repetition code. If source messages are encoded in the information code, which has a code word length is k, then such code has no error capability, control capability, its minimum distance is 1. In a repetition code, each bit of the information word is repeated q times. So instead of 0 we have q times 0, instead of 1 we have q times 1. For example, if q is equal 3 and the following information word, then this one goes and we have triple 1, this 0 is triple 0, 1 is triple 1, 0 is triple 0. And we obtain the following code word. The code word length is length of information word multiplied by q equal 3. The minimum distance of repetition code is q. Then code corrects up to TC errors. This comes from this inequality, or detects with no correction this number of errors, or detects with correction this number of errors. Okay, everything is fine. We have improved the error control capability, but the code rate is very low. The code rate is 1 over q, and this is the bad side of this repetition code. Decoding is done using the so-called majority logic detection. If q is odd number, then if the weight of the received word is less than TC or equal, then we may correct this to 0, and if greater than TC to 1. This is an example, q equal 3, so all sequences with 1, 1 or triple 0 are detected as 0. All sequences with double 2 1s and or triple 1 is detected as 1. If q is an even number, then also in case we have the weight of the received word is q divided by 2, we don't know whether it is 0 or 1. We have detected the fault but not corrected. It is impossible to correct. Okay, Hamming codes is the next screencast.